Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is almost the last video in a series on graphing using calculus. I just like to do a lot of examples for this, mainly because, well, it involves a lot of algebra. It's good to see everything that you could possibly see in this style of problem. So let's go ahead and hop into the graphing. If you haven't read my how-tos, or if you haven't seen this how-to video on how I derived this, you should go back into my video series and watch that. But otherwise, let's get started. And if you're keeping track of my numbering system, you'll see that I skipped an example. I only skipped an example because I've done enough, right? Graphs, I've done quite a few. So I just wanted to do this one right here because this is a really cool one. All right, let's go through and talk about all the little pieces here. Let's see, y-intercepts. Well, or intercept. There, you shouldn't pluralize y-intercepts. You can only have one for a function. All right, so when x is 0, what do we get? Well, if x is 0, we get 1 minus 0 plus e to the first. So 1 plus e. That's as good as it gets. There's really not much else I could do with that. Let me double check my math. Yep. So I'm going to go ahead and make a table over here, x versus f of x. And we have 0, 1 plus e. If you want, you could go ahead and grab a calculator and you could find that 1 plus e is actually it's 3.71828, and so on and so forth. But I'm just going to round to 3.7. All right. And the x-intercept or intercepts. Now, this is a great example of when you should know when to walk away and when to run. I don't know why that came up. In this case right here, to find our x-intercepts, as you know, you should always let the function be 0. But if you did that, you'd be trying to solve an equation that has a mixture of algebraic and transcendental functions. There is a way to actually solve this, to approximate the solution to this by hand. It's called Newton's method, and that's a method that I actually teach my students, but only after we go through graphing. So in this case, there's just no way you could really get a good value of what the x-intercept here is. So as I would normally tell my students, if it's impossible to really compute it analytically by hand, then you can skip it. So in this case, I'll just skip finding the x-intercepts. It is possible, you can totally do it using Newton's method, but I'm not going to showcase that right now. Maybe I'll include this example in my lecture video on Newton's method in the future, but I'll just say too hard. Now, let me just let you know, saying too hard is not an answer on an exam when it comes to every question. You can't just say, this question is too hard. But in this case, finding the x-intercepts by hand, yeah, that's a bit too hard. Although you could use intermediate value theorem to approximate the interval, but I'm not going to do that. The domain. Now, the domain of this function is all real numbers. And that's pretty easy to see. It's a linear function plus an exponential function, all real numbers. The next thing, symmetry. Well, I'm going to tell you that there's no symmetry here easily because it's an exponential function, but let's go ahead and verify that. F of negative x is 1 plus x plus e to the 1 minus x over 3. There is no way at all that you can factor out a negative or some silliness like that to make this become plus or minus f. So this is never going to be plus or minus f. Thus, there's no symmetry. The real big clue that there's no symmetry, honestly, is that exponential function. But there are some modifications you can make to an exponential function to make it symmetric, like an absolute value, or, well, no, not even that. An absolute value on its argument. Now, that's another story. But anyway, let's go ahead and move forward. So we've taken care of y-intercepts, I see there, I pluralized it. Y-intercept, x-intercepts, domain, symmetry. Now let's talk about asymptotes. Vertical asymptote, none. Domain is all real numbers. Don't have to worry about that. Horizontal asymptote. We actually might have a horizontal asymptote here, just to give you an idea. Actually, you won't. Now I'm saying it out loud, because as x goes to infinity, that will never become finite. As x goes to negative infinity, that will never become finite. However, so that's me just saying you don't have a horizontal asymptote. However, so I'll say none. Oblique asymptotes or slant asymptotes, you do have. Now remember, the definition of a slant asymptote is that you have a slant asymptote at some function y if your function f minus that y tends to 0 as x goes to infinity. In other words, the limit as x goes to infinity or negative infinity of f minus y becomes 0. That would imply that y is your slant asymptote. Or if it's negative infinity. It doesn't have to be both, just one or the other. It could be both, but one or the other. Well, let's take a look at this. As x runs off to infinity for this function, you can see it's 1 minus infinity. And does this disappear? No, that blows up, right? E to the infinite power. So we do not have an oblique asymptote in the positive direction. However, as x goes to negative infinity, well, this doesn't disappear, but e to the 1 minus infinity is e to the negative infinity, which does tend to 0. So that will actually disappear as x goes to negative infinity. So we do have an oblique asymptote. So we are going to claim that our slant or oblique asymptote, I don't care actually which you say, I'll tend to call it oblique, but our claim is that y equals 1 minus x is the oblique asymptote. I'll spell it out. You can get in trouble if you try to shorten that. So claim y equals 1 minus x is the oblique asymptote. Here's the proof. Proof. Limit as x goes to negative infinity. By the way, it's oblique as x goes to negative infinity, not as x goes to positive. The limit as x goes to negative infinity of f minus this 1 minus x that we're claiming is the oblique asymptote, well, that's going to equal the limit as x goes to negative infinity of 1 minus x, was it plus or minus? Plus e raised to the 1 plus x over 3 minus the quantity 1 minus x. You can easily see the 1's will cancel. The x's will actually cancel as well. And you get that e to the 1 plus x over 3 as x goes to negative infinity. That tends to 0. That is the proof. Very, very, very fast. You just want to showcase that you know what an oblique asymptote is. So you want to showcase to your professor that, yes, I know the difference between my function and my claimed asymptote tends to 0. Therefore, that claimed asymptote is an oblique asymptote. So now that we have that, I'm going to highlight it, otherwise I'll forget it. We now can step into the calculus. The calculus, we need y prime, right? Luckily I have y written right here. Let me turn off that ruler, I just saw it. So a y prime, I'll show it up above, why not? Y is 1 minus x plus that exponential. The derivative of 1 is 0. Derivative of negative x is a negative 1. Plus the derivative of e to the 1 plus x over 3 is e to the 1 plus x over 3 times the derivative of its argument, which is the derivative of x over 3, which is 1/3. So our derivative is negative 1 plus 1/3 e to the 1 plus x over 3. We want to know when that doesn't exist or when it's 0. It's an exponential function. It always exists. But y prime is 0 when 1 is equal to 1/3 e to the 1 plus x over 3. All I did was set this equal to 0 and started solving automatically. Multiply both sides by 3, you get to that. Take the natural log of both sides. You get the natural log of 3 is equal to 1 plus x over 3. Subtract 1 from both sides and multiply both sides by 3, and you'll get the following. 3 times the quantity natural log of 3 minus 1 is equal to x. That is where our derivative is 0. You can go ahead and grab a calculator to approximate that. It is roughly 0.3. So I'm going to go ahead and say that this implies x is approximately 0.3. We might need some more accuracy on that, but we'll find out as we move forward. Here's my number line. Oops, not yet. Now there's my number line, y prime, and I'll just plot in here 0.3. Prior to 0.3, is our derivative positive or negative? Like at x equals negative 3 trillion, for example. At x equals negative 3 trillion, this is basically 0. Minus 1 is negative. So there you go. I happen to know my derivative is negative here, or you could have plugged in 0, by the way. And so my function is decreasing. Try a number that's super huge, like a billion. Well, you'd have e to a massive number, which is positive. Minus 1 is still positive. You know your function must be increasing. This right here gives us a point that we can put in our table. Also, it gives us a local min. I'm going to put that point in our table, roughly 0.3. It's not exactly 0.3. And I'm also going to evaluate the function at that value. Since I have it saved in my calculator, it's just safe to do it right now with the answer button. And I get roughly 3.7. So that'll be useful. Now we're going to go ahead and do the second derivative down here. Our first derivative is this mess right here. Second derivative actually will be a bit nicer. Y double prime is going to equal 1/9 e to the 1 plus x over 3. That was supposed to be a 1. It just kind of got out of control there. But you could check my second derivative, but that is true. That always exists, and exponentials never negative. In fact, never 0. So therefore, y double prime is never going to switch signs. So it's either always positive or it's always negative. And in fact, exponentials are always positive, so we know our function's always concave up. There's not a lot going on with the information in this other than what's the cool part, the oblique asymptote. So now I will go ahead and pause the video and draw in my axes and my number lines up above, and then we'll start into the graph. Okay, as you can see, I've kind of labeled everything out here. A couple things I did do as well. I didn't see it until I started labeling, but our y-intercept and that local minimum had the same value, right? 3.7. So I had to expand those digits a little bit. The y-intercept occurs at 3.71828 and a bunch of other numbers after that. And the local minimum occurs at 0.3, 3.704 and some numbers after that. That is definitely lower than 3.718, but not too much lower, right? So I have labeled y prime and y double prime, the number lines up above. I've also stated where we have our local minimum, where we're decreasing, increasing, all that other fun stuff. And probably the most important part of this graph, the oblique asymptote, easily forgotten. So be very careful about that. I'm going to go ahead and go over to 0.3 here and plot a point at a height of 3.7 and some change. And I did not mean to drag that out of the way, so I'm going to go ahead and do that one more time. So here we go. And 3.7 is probably right around here. Okay, I'll put a little dot right there. And I might even lower that a little bit just because I want it to be slightly lower than that. So there we go. We'll say this is 0.3 comma 3.7, and let's see, I'm going to express this in a few more digits, 0.4. We'll do that. That's our local minimum. Our y-intercept occurs just barely above that, to be honest with you, and that occurs at 0.3.718. Again, just significantly rounding, but whatever. Now remember, our curve is always concave up. It's decreasing until we get to this point right here, and then it's concave up and increasing after that. Now the concave up and increasing after that is easy because, well, there's no guideline, so I can just kind of say it increases like this, and it does because it's exponential. But to the left is really hard. It wants to get close to that asymptote. I'm actually turning my computer as I do this so that I can draw this appropriately. It wants to be concave up, and it'll eventually reach that asymptote. You can see that my hand is hitting edges here, but it'll eventually want to get to that asymptote, but it's incredibly difficult to do. I think probably the best thing for me to do is maybe lower that point slightly so that I can aim a little bit better. I didn't mean to erase my asymptote or my y-axis, so maybe I'll plot it right there and just have it this. I just would like to eventually get really close to that asymptote. It's just going to be incredibly difficult. It takes a long time. Let me pause the video and see if I can do it. I think that's as good as I can get on that. That's a really tough one to get because those oblique asymptotes are tough to approach if you have a concave up like this and it's bending away from it but getting close to it. It's really weird to do, but there you go. That is a full graph of it. We've labeled the local minimums. We've labeled our intervals of decrease and increase. I didn't actually, in any of these videos, mention labeling the intervals of decrease or increase, but you know how to label an interval. It goes from negative infinity up to roughly 0.3. That's your interval of decrease. Your interval of increase goes from 0.3 to infinity. And then your interval of concavity, it's concave up on all real numbers. So those are kind of little things that you should know how to do already, so I'm not really super concerned about that. Other than that, we are completely done.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.